Move to the next speaker, our third and final speaker for the session. I see that she's already on screen, ready to jump in. Kaymie Shiozawa from the grad student, supervised by Prof. Neville Ogand at the Eric and Evelyn Newman Laboratory of Biomechanics and Rehabilitation at MIT. And our talk is titled Frequency-Dependent Force Direction Elucidates Neural Control of Balance. Thank you very much, Kaymie.
Okay, thank you for the introduction. I will share my screen. Is the screen visible? Okay, great. Okay, so human balance is an unstable task that requires the control of translational and rotational acceleration. In general, we use foot-ground reaction forces to manage these accelerations. Previous work measured balance in humans and identified a point of intersection of foot-ground interaction forces that exhibited consistent frequency-dependent behavior across multiple subjects. Because the height of this intersection point relative to the center of mass dictates the relative directions of translational and angular accelerations, the intersection point provides a compact geometric representation useful in understanding the dynamics and control of human balance. To test whether the intersection point's frequency dependence observed in humans was a distinctive signature of neural control or was a necessary consequence of biomechanics, this study simulated quiet standing and compared the results with human subject data. Separating the neural contribution from biomechanical factors by only observing human motion is challenging. So to simulate balance, we estimated the human body as a double inverted pendulum that is controlled by an LQR controller. A key feature of LQR control is that a cost function is minimized and the result always yields a stable controller. The parameters of interest were alpha, which penalizes the relative cost on the state deviation versus control input, and beta, which penalizes the relative cost on the control input in the ankle and the hip joints. We added noise to the hip and ankle joints to replicate the variability observed in human quiet standing. So alpha, beta, and sigma r were the parameters we varied to match the simulation data to human data. Before we get into the results, I will define the intersection point that I've been mentioning. If estimating the ankle as a pivot, there is a ground reaction force acting there along with the ankle torque. This is equivalent to a ground reaction force acting at the center of pressure, which is some distance away from the pivot. Assuming that there are two net force vectors in time that are defined by their direction and point of application, we define the intersection point as the height of the position or the extension of the two force vectors crossed. With a little bit of math, the intersection point relates to the center of mass, center of pressure, and the orientation of the ground reaction force in this way. The center of pressure and theta f were bandpass filtered into 38 frequency bands to find the intersection point at each band. 40 trials for each varied parameter were run to allow for statistical analysis of the results. This is a simulation data that best replicated the human subject data overlaid on top of the human data. Before getting into the best fit parameters that I found, we saw that for all stabilizing controllers, the intersection point followed a trend where it was above the center of mass at low frequencies and below the center of mass at high frequencies. Because changing the controller parameters didn't alter this general trend, it most likely signifies a necessary contribution of biomechanics. However, the frequency at which the intersection point crosses the center of mass, denoted by this value 1 in the y-axis here, or the high frequency asymptote of the intersection point varied across different tested parameters. For example, varying alpha affected the frequency at which the intersection point crossed the center of mass. A large value of alpha, such as 10 to the 6th or 10 to the 4th, minimized the control input required to stabilize the inverted pendulum, and resulted in a close replication of human subject data. This makes physiological sense because humans likely minimize control effort during quiet standing. Varying beta also affected the frequency at which the intersection point crossed the center of mass. Beta is less than 1, where there was more penalty in the hip torque, resulted in close replication of human data. This also makes physiological sense because during quiet standing, humans primarily use ankle torque to balance. Lastly, varying the noise ratio affected the high frequency asymptote. The noise ratio that was slightly less than 1, 0.9, where there is more actuation noise in the hip, resulted in close replication of human subject data. So in conclusion, we successfully distinguished the biomechanical constraint, where the intersection point declined with increasing frequency, from the neural strategy, where humans tend to minimize control and penalize the use of the hip torque more than the ankle torque. This method that I just presented can be extended to different experimental conditions, such as sagittal and frontal plane balance, with and without assistive devices, and in aged and impaired populations to identify differences in control or characteristics employed by humans. Thank you.
Thank you. Thank you very much. Really clear, even though I know nothing about it. So I'm probably going to have very naive, silly questions. So if anyone else wants to jump in with something more. Also, it was very ironic to try and listen while I'm trying to balance myself and clearly doing a terrible job. But my first very naive question is, why did you choose as a model for the human, the double inverted pendulum? Like, it's something that is known in the literature that is the ideal model?
Yeah, great question. So actually in balance, some people use a single inverted pendulum as well. And having, of course, the single inverted pendulum is more simple. It simplifies the whole model more, but we actually found that the single inverted pendulum could not reproduce this. Oh, can you see my cursor?
Yes.
Okay, yeah, so it could not reproduce this intersection point frequency dependence where it goes below this dashed line, the center of mass. At high frequencies, it actually converged at above the center of mass at high frequencies. And we just solved that mathematically. And so the single inverted pendulum was kind of out of the question. And so the next simplest model in that case was the double inverted pendulum.
I see. This makes sense. And so the fit with the human data is impressive. Could you remind us how was the human data collected and what's the sample we are talking about? And that's potentially how you might want to compare to other samples, but in this case. Yeah,
so I actually didn't collect the human data. It was done by researchers at University of Wisconsin-Madison. But the human subjects were healthy, young subjects, I think at under 30, and there were 10 subjects, and they were standing without any external perturbations on a force plate to measure the force vectors and find the intersection point as shown here.
Right. And so you were mentioning that a possible development of this project would be to try and apply this model to other other population that really seems to be the main topic of this session.
Yeah, I think I'm quite interested in developing assistive technologies for impaired populations, and I think understanding the neural control and the dynamics of impaired or just people in general during balance is an important first step to that. So I think that if we could apply this method and find neural control strategies for people who use assistive devices or aged and impaired populations, that could inform the design of future assistive and rehabilitative technologies.
Could you perhaps elaborate a bit on this minimal control solution? Like, what do you exactly mean, and how do you ensure that it's actually been met, like that this solution has been met?
Yes, so so here, what Val is talking about is this minimal control solution that I found to be one of the best fit parameters. And this happens when alpha is greater than 10 to the fourth. I actually have a maybe useful slide here. So this kind of gets into control theory a little bit, but the essence is that basically when you're stabilizing a double inverted pendulum, it's inherently unstable because it will fall with gravity. So you're trying to move these open loop unstable poles to the left side of this dashed line here. And then when you apply a minimal control solution where alpha is a fairly large number, such as 10 to the 6 here, then we see that the poles get directly mirrored across this dashed line. So the red crosses are directly above the black crosses here. However, as alpha starts to decrease and it's no longer in the minimal control region, then you see that the poles start to deviate away from the mirrored position of the poles. And that's how we ensure that we are in that the minimal control solution yields results similar to human subject data, and how we inferred that humans probably employ a control strategy that minimizes their control effort.
I see, I see. I don't want to force you to stop sharing, but if any one of the other speakers and the other panelists wants to come back on screen and ask questions, they're welcome to do so, as well as if any of the attendees want to type or come on stage to ask their question. I know I keep bugging you about your model, and you explain very well the pendulum. I'm convinced, but why a linear controller? Is that justified? Or
yeah.
could you? Yeah.
So I used the linear controller because in quiet standing, which the human subjects were not subjected to any external perturbations. So in quiet standing, humans only deviate about a very small angle about the center position, about the upright position. And so I think the linearization is justified. Although I used a nonlinear plant here, and then just applied a linear controller here. And we also saw that when simulating, the center of mass did not change its height very much. So that also says to how much the pendulum deviates about the upright position. It doesn't really deviate about the upright position, basically.
Okay, so just for me, the 20 friends we have here and the 100 people that are following on YouTube, we are going to keep it quiet. But are you happy with this model, or if there's anything you would like to tweak? That you haven't tweaked yet, and it's going to be your next.
Yeah, I think right now we've only added actuation noise to the joints. There's much more complex sensory noise, measurement noise, things like that in actual human data. So those could be some next steps, some ideas for next steps.
Sounds very exciting. I also know I would be a terrible subject because, as you can tell, I'm unable to stay still. But yeah, so I have definitely learned a lot from these 3 talks and amazing session. If anyone has any last questions or any last comment. Oh, we do have one last question. I did well in asking. Reza is asking, what would happen if you have signal dependent noise?
Signal dependent noise.
And by the way, Reza, if you want to talk, if you want to explain your questions live, we can even bring you. Sure. Okay. Let me get.
Okay, great. Yeah.
Hi, Kaymie.
Hi.
Thanks for the good talk. I was just wondering if any of these intersection point heights would change if you have a noise value that scales with the size of the torque. That's what I meant by signal dependent noise. Because in the
Yeah.
motor control literature, usually people argue that the neuromuscular noise increases by increasing the force.
Yeah, exactly. So actually, what troubled me the most, the result that troubled me the most is that here, I found that sigma r is less than 1, where there's more noise in the hip, resulted in the best fit parameter for the noise ratio, and that was a little counterintuitive to me and counterintuitive to the previous work that you mentioned, Reza, because I found in from data that humans likely use the ankle more than the hip, and so it didn't really make sense that there was more noise in the hip, even though we were using the ankle more. So I think that, like I said before, I think that could be a result of just simulating using actuation noise here. So perhaps I think that's why an important next step could be to add sensory noise to account for all sorts of different noise inputs.
Right. We live in a much more complex world than than any model can understand yet. I'm sure we're going to get there.
Yeah, but I think that simplifying to glean some insight is important, even though it can't capture all of the things.
Absolutely, and I loved how you explained that you tried a model, like the simplest model, and then if that doesn't work, you can add a piece and make it. You make it complicated as you need it, not more than.
Yeah, exactly.
Well, unless anyone else has a very last question, I'm gonna thanks again our 3 amazing speakers and all of you for attending.